All right, let's get right into it. We're going to talk about a process that is really at the very center of the nuclear age. It's something that holds the key to both incredible amounts of clean energy and, at the same time, the world's most powerful weapons. So let's pull back the curtain and demystify uranium enrichment.
In this quote, it just nails it, right? The entire process, the whole reason it's so sensitive, comes down to this dual nature. You got a technology that walks this incredibly fine line. And if you want to understand modern geopolitics or energy policy, you have to understand where that line is.
So you might be wondering, why do we even need to do this? I mean, why can't we just dig uranium out of the ground and use it? Well, the whole challenge, the reason this entire industry exists, comes down to the atoms themselves.
See, when you mine raw uranium, you're actually getting two main types, or isotopes. Think of them like atomic siblings. The first one, uranium-238, makes up almost all of it. It's super abundant, very stable, but it's not really useful for a nuclear reaction. Then you have its much rarer sibling, uranium-235. Now this one is the magic ingredient. It's fissionable, which is just a fancy way of saying its core can be split apart, releasing a massive amount of energy. So U-235 is the engine, and U-238 is pretty much just along for the ride.
But here's the kicker, the part that's truly astounding. In all that uranium you just mined, only 0.711% of it is that useful U-235. That's it, less than 1%. And for any kind of sustained nuclear chain reaction, whether you're talking about a power plant or something else, that number is just way too low. And that is the fundamental problem that enrichment was invented to solve. So how do you do it? How do you raise the concentration of that one crucial atom? Well, that brings us to the ingenious and, frankly, incredibly difficult industrial process they came up with to separate these two atomic siblings.
Okay, so the most common way to do this today is with something called a gas centrifuge. First, you take solid uranium, and you have to turn it into a gas. Then, you pump that gas into these tall, skinny cylinders that spin at literally supersonic speeds. We're talking about generating incredible G-forces here. Now, remember how U-238 is just a tiny bit heavier than U-235? Well, that intense spinning is enough to push those heavier U-238 atoms out towards the wall of the cylinder, while the lighter, more valuable U-235 atoms tend to hang out closer to the center. You then skim off that slightly more concentrated gas from the middle, and you feed it into the next centrifuge, and the next, thousands of times in what's called a cascade.
So after all that spinning, after all that work, what do you actually end up with? Well, it all depends on how long you keep the process going. Let's take a look at the different grades of uranium you can make, because each one has a very different job. Okay, so this is our starting point. This is natural uranium, straight out of the earth. As we know, it's got that tiny concentration of U-235, just 0.711%. You can't do much with this.
But you run it through that centrifuge cascade for a while, and you get this, low enriched uranium, or LEU for short. As you can see, we've bumped up that U-235 concentration to somewhere between 3 and 5%. This is the stuff. This is the standard fuel for pretty much every commercial nuclear power plant lighting up our cities all over the world.
All right, but what if you keep the process going even longer? Well, then you get something called HALEU. That's high-assay, low-enriched uranium. Now we're talking about a U-235 concentration between 5 and 20%. This is a much more potent fuel, and it's being developed for a whole new generation of smaller, more advanced, and more efficient reactors.
And here it is. This is the final and most critical jump. If you let those centrifuges run for a long time, you can push that concentration past 90% U-235. This is highly enriched uranium, or HEU. And here's the point that changes everything. This material is pure enough to power naval reactors, think submarines and aircraft carriers, and it's also the essential ingredient for a nuclear bomb. The pathway is the same, even though that last leap from reactor fuel to weapons-grade material takes an enormous amount of extra work.
And that single fact, that the same path leads to both clean energy and a weapon, is exactly why this isn't just a physics lesson. It's a story about global security. It's the reason this technology creates such an incredibly delicate international balance.
You know, the biggest worry, of course, is proliferation, making sure that this peaceful energy technology doesn't get diverted to build weapons. That's why international bodies have teams of inspectors to monitor enrichment facilities around the clock. It's why places you hear about in the news, like Natanz and Fordo in Iran, become these huge political flashpoints. And we can't forget the byproduct. All that leftover U-238 is called depleted uranium. It's incredibly dense, so it's used for things like armor-piercing shells, but it's still radioactive, which raises a whole host of health and environmental concerns.
So it all comes down to this really fundamental question, doesn't it? The science of enrichment gave us a single key that can open two completely different doors. One door leads to vast, carbon-free energy. The other leads to unimaginable destruction. The technical process is all about separation, but the real global challenge is one of control, of policy, and ultimately of trust. It forces us all to ask, when you have a key like that, who gets to decide which lock it opens?